Hello everyone, welcome to my talk, which is called Distributed Locking in Java. I'm Rafal Leszko and I'm really happy to be able to speak to you. So, before I will discuss all this topic, I would like to tell you a few words about myself. So, I'm an engineer, mostly focused on the cloud domain and distributed systems. I worked at Hazelcast, Google, and CERN, and some other organizations. I'm also an author of the book Continuous Delivery with Docker and Jenkins, and from time to time I do conference speaking or trainings, but on a daily basis I'm an engineer. I develop software. And that's what I love to do, and that's what I do every day. I live in Krakow in Poland. So our talk will be today about distributed locking, and here's the agenda. So it's pretty straightforward. So at the beginning there will be a short introduction about distributed locking in general, and then I will walk through different approaches in the context of Java. We'll walk through the simplest possible scenario, which is not 100% correct, but it's good for some use cases, and then we walk through to end up with 100% correct fenced locking solution. While I'll be talking, I will also always describe you the solution, the problems you can have with it, and I will always give you the trade-offs, because there is no one single distributed locking mechanism that you should use. And I will always show you an example in Java, so how we can use it in Java, but some of the solutions applies to other languages as well. And for the full scenario, I will show you an example using Java application running in Kubernetes, but it doesn't matter. It can be run anywhere. It's just the simplest way to present it is to deploy our cache manager in Kubernetes. Okay, with this agenda in mind, let's start with the first thing I would like to tell to you, which is the introduction. So, it's hard to do the introduction to distributed locking because almost everywhere where you will look on the internet, people will tell you the same. Don't use distributed locking. Distributed locking is a bad idea. But still there are some scenarios in which you will need to use it, or some scenarios when it actually makes sense to use it. And that's what I would like to stress. So there are two reasons why you can use distributed locking. So the first one is efficiency. So you use this, you don't really need it, but it improves the performance. So it prevents some executing some work more than once, so you do a lock, or it's just you can treat it as an optimization. Like a cache, for example. Cache is also an optimization, but you don't need it. The same with distributed lock. So that is the first use case of distributed locks. But the second use case is correctness. So you need this lock to prevent data corruption, data loss, some inconsistency. And failing lock can result in some serious problems. So it can make your system inconsistent, which is a big issue. And it's very important to know which use case you are addressing with your distributed lock. Because depending on which use case you have, you will choose a different solution. So that is why you may need distributed lock in your system. You may not need it. If you can live without it, it's probably better, but in a lot of cases you will see that you will need it. And these are two reasons. Now, how it actually works, how the distributed lock actually works. So, we usually have two or more applications running concurrently and using the same resource. And we would like to make access to the resource like kind of a mutex. So it's only accessed by Y application at the time. So if one application A1 wants to use the shared resource, it first sends a request to the lock manager service, and the lock is acquired. Then it can use the resource, so write some data. Then it says, okay, I'm done, I unlock lock. Then the second application can lock it again. It holds the lock, write something to the shared resource and unlock. So that is like a happy path. That is how you would like it to work. But if you think about it, like this scenario does not really differ much from the like non-distributed lock. So you acquire a lock, you use some shared resource, you unlock, you release the lock. However, the fact that it's run in the network, it is a big thing actually. That's why you should use locking, but not necessarily distributed locking. Because like consider what would happen if application 1 would crash at some point, which may happen. So imagine like application 1 acquires the lock and then it suddenly crashes. So nobody else could use the lock in result, and our system becomes unavailable. So that is why, like in any distributed manager, the lock is obtained for the given time. It's called a lease. So after this time, even if the application does not interact with the lock manager, the lock expires. So even if application 1 crashes, in every distributed lock mechanism, there is always a timeout after which the lock expires. So even if the application 1 crashes, it's not such a big deal because the system can recover. The lease is expired and the second application after some time can acquire the lock, write to the shared resource and unlock. So that is our context. So that is what I presented is already like one difficulty of the distributed lock against normal non-distributed lock and how we cope with this. But like this lock manager, it can be implemented in this lock manager service can be implemented in different manners. And there are different possibilities, and now we go to the main part of the talk, meaning how you implement lock manager. Because that's so far what I told you, everything applies to any scenarios with distributed lock. Every distributed locks work this way. Now there will be different. So the first thing how you can implement the lock manager is to use like a single instance. So you use like single instance of lock manager, and then every application uses this instance to acquire the lock. In this scenario, on this diagram, I presented with Hazelcast because I worked with Hazelcast, but it can be the same with Redis. The idea is the same. You run a Redis instance, you acquire a lock on Redis. But I will continue the example with Hazelcast, but remember it doesn't matter so much. So we acquire a lock by addressing a single instance lock manager, and in the code it looks something like that. So we connect with the Hazelcast client to the Hazelcast server. We get a lock, then we execute lock, do some exclusive operation, then unlock. That's it. How we run the server? I will present you how to run it in Kubernetes, but you can run like no matter if it's Hazelcast or Redis, you can run it and then different manners. It's just Kubernetes, I think, is the simplest one to present at this talk. So I will run the log server, which is Hazelcast instance, and then run two applications, and you will see how they acquire a log and use the shared resource. So this is our code, exactly what you've seen on the slide. As you see, writing to the shared resource, I will just simulate it here with some print lines and the sleep. It doesn't matter at this point what is the shared resource. So that is your Java code. And By the way, a link that I will share with you is to this repo, and this repo I will show you this at the end of the talk. But this repo, I really recommend you going to this repo, and you can then try it step by step, really on your own, different distributed locking mechanism. So in this talk, I will just copy the commands here. So the first one is to start the Hazelcast, which will be our lock manager. So if we run this, it should run lock manager in Kubernetes in our scenarios. So we can check if it's already running. So it's already running. We can check Hazelcast logs. If nothing bad happened, it looks healthy. It created like single instance of Hazelcast. Now we are ready to run our two applications. So these two applications, I'll also run them in Kubernetes, but this application is nothing more than Dockerized version of this one. So if I run two applications, we can see that they are running application 1 and application 2, and we can see what happens if we check the logs of application, and the same check the logs application 2 and see how they interact with the log. So you can see that, you know, it's always one of the application is writing to the resource. They're never writing at the same time, and that's the whole idea of the locking mechanism. So far so good. So you see how it works in practice. We can clean it all up and move on. So this is our so this is exactly the scenario we did. All works good. Obviously our log manager support leases, so there's no problem if one application crashes. However, there may be another issue. If you look at this diagram and look on of what we did, there is one other issue. In any distributed system, always anything can fail, anything can crash, but your system should still be highly available. But our system is not highly available, because if our single instance of the log manager crashes, suddenly no application can acquire the log, and so use the shared resource, which is very bad actually, because we cannot do anything in our system. So that is the problem of the single instance. And now, depending on if you use single instance as a log manager, so now depending on your use case, you will either at this point not to allow shared resource or allow it to everyone. That will be your business decision, business driven decision what to do in such scenario. But your log manager can be down at any point of time. So yeah, so this is usually single instance will be good for efficiency is in mind, because maybe you just don't want to repeat the same task. But okay, if from time to time your log manager is down, maybe you will repeat the same task and it's still okay. But you cannot rely on this, never rely on this in terms of correctness, because in every distributed system any part can be down. Short summary of the single instance distributed logging. So it's usually very good for efficiency. It's very good performance-wise. Very simple, but it's definitely not a fit if your use case for distributed log is correctness. And this correctness part is something we'll try to improve with other implementations of the distributed logging manager. So one improvement, if we have one instance that can fail, so let's try with multiple instance. So to use multiple instance instead of the single instance for the log manager. So in case of Hazelcast, we can use Hazelcast cluster instead of a single Hazelcast instance. So again, the diagram is similar. the application, they just don't use a single instance, they are connected to every instance in the cluster, and if some instance is down, they can still use the locking mechanism because the data in the cluster is consistent, so even if one is down, our lock is still okay. So how we can use it in practice? Show me the code. So if you look at the client code, it's the same. We didn't change anything in the client. The address is the same. We give the address of the cluster. However, there's a different way how we deploy our log manager, because we deploy a cluster, not a single instance of Hazelcast. And let me show you how it looks like. So again, let's clean this up, and again, let's go to our GitHub. So this is how you can start the whole Hazelcast cluster. On Kubernetes, the simplest is to use Helm, but it's not part of this talk. It's the important thing for you, even if you don't know Kubernetes, is that now we will be running multiple instances of Hazelcast instead of just one instance. So if we see the logs of our log manager, one member is already created. We are still waiting for another members to join. In the meantime, if we look at the application code, it's still the same. We specify the address of the cluster and everything else exactly the same, no changes. Here we need to wait until all pods, so all members are up and running. So the second one started. We will wait for the third one, and he has already 2 members, and in a second the third members will connect. And in the meantime, these commands are exactly the same as before, so we are running 2 applications which are doing the same, just locking and trying simulating to write something to a shared resource. Still waiting for the third member. Yeah, the third one is running, so they form in a second. They should form a cluster of 3. So yeah, this means that Hazelcast members, they formed one cluster, which means that we can run our 2 applications. And if we check the logs of the first application and logs of the second application, you should see that, you know, they so nothing different in the log. But now if you if we check one thing, so you know, this is the result is the same as before. But now if we delete one of the members, so we simulate crash of crashing of one of the log manager nodes, you see that they are still working. Before in a single instance they would stop working, but here no problem with that. So even if one member is down, there's no problem, the log is still there. Let's do a cleanup and continue with the talk. Yeah, so what we did is like we create from a single instance, then we created multiple instance, but so we are highly available now. But actually, like if you think about it, it looks good. I mean, this looks convincing that we could use such a cluster for a distributed log, but there is still one problem we didn't think about. And imagine the following scenario. So crashing of a single log manager node, so a single Hazelcast member, is not a problem. However, we can have another problem, like this one. What would happen if we have no crash, but just network partitioning? And even worse, if one application is in one network partition, another application is another network partition, then actually they can do log at the same time, and they can acquire log at the same time. This seems like an issue. This is called a split brain, and it can, you can have some in Hazelcast, for example. There is something called split brain protection. So the cluster, Hazelcast cluster, can protect you against split brain, but it still takes a few seconds. So it would mean that you accept having lock in two applications for like a few seconds, which usually is bad if correctness is your use case again. So this network partitioning will still try to improve. But before that, a short summary if you use multi-instance lock manager for distributed locking. Obviously, it's good for the efficiency case. It's a little better for the correctness case, but it's still not acceptable in most cases for correctness. It's a little better than single instance, but not that better. Little more complex than single instance, but not that more complex, and it's still very performant, no matter if you use Hazelcast or Redis or any other tool. But okay, like I promised you, we will improve this. So this is not perfect, this multi-instance lock. So in terms of correctness, so we need to improve. And one of the improvement is a red lock algorithm. So red lock algorithm is like it's related to Redis. So it was designed and implemented for Redis. And in the red lock algorithm, we have a number of independent Redis instances. They are not cluster. It's not Redis cluster. It's like they're independent Redis nodes on separate computers, separate machines. And the algorithm is like on the client side, you try to sequentially acquire lock on every instance, and if the majority of instances confirm the lock, then you have the lock. So the lock is only acquired if the client was able to acquire the lock on the majority of your Redis instances. So if one instance is down, it's not a problem, because your application 1 will acquire the lock on the instant Redis 1 and Redis 3rd, and that's the majority. We are still fine. Also, what happens if we have network partitioning? Let's look. It's not a problem, because application 1 will acquire the lock on this first and second instance, so it knows that it has a lock. Application 2 will acquire only on the third instance, it will know it's not the majority. So it knows that it cannot use the shared resource. So looks great. How it looks like in practice. So on the server side, we need to have 3 Redis instances. If we stick to the Kubernetes, that's how you can run 3 independent Redis instances. For the application part, this is like a Java example. So you can use Redison library for redlock, give 3 Redis instances, get 3 separate locks on each instance, and then acquire a lock before writing to a shared resource. Okay, let's go to the demo part. So let's first check if everything from the last part was cleaned up. It looks good. Clean it up. So we start our red lock. We start 3 separate Redis instances on Kubernetes, like this one. kubectl get pods. We can check if they are started successfully. Should be fine. Yeah, server initialized. Ready. Looks healthy. How does the client code look like? Redlock. So this is our client code, the same as on the slide. So we take actually so we create like 3 Redis clients and put them in one Redis on Redlock, and then acquire the lock and write to the shared resource. So again, let's run 2 applications and see how they behave. Kubectl ctl logs. Now it's we need to check the logs of the application. This is the first application, second one. So yeah, they work fine. We should be able to kill one Redis and see what happens. So let's try to kill this one, for example, the first one. I think it should still work fine. Let's try. They stopped for some reason, but normally they should still work. I think it's just here. They should still work because the majority is still there. So let's clean it up. Yeah. So this red log algorithm it's kind of like you know, you take like you need like majority on the client side, but the server does not even know about what's going on. So it's pretty good. Actually, a lot of, you will see like red log is used in a lot of places, and a lot of places for the correctness reason. So it's like considered somehow like a standard for distributed logging in a lot of places, a lot of systems. However, believe it or not, there are two issues with the red log algorithm. And these issues actually mean that this algorithm should not be used for correctness in the production system. But let's talk about these issues. So first thing is that red log requires server clocks to be in sync, at least to some extent. It does not look that difficult at first, but actually syncing the clocks across servers is a difficult thing, and it's not so easy to have clocks really in sync. So this is one issue of the red log. The second issue is even worse, and let me explain what is the second issue. Second issue is like that log and write are not atomic. They are not like transaction based. So let's see what can happen. So application 1 acquires the log. So far so good. The log is held by application 1. There is some lease time. Everything is good. But now every application process can be blocked for some reason. I don't know. You can have like stop the word garbage collection or anything. I mean, it's not predictable what happens in your application. So if the application process is blocked for some time, okay, lease expires, so application 2 acquires the log, it writes to the shared resource, but then application 1 wakes up and it writes to the shared resource because application 1 thinks at this point of time that it acquired the log. And that is a problem. That is a big problem actually, that corrupts the correctness of this whole algorithm. So before we go to the solution, let's first see like a short summary of red log. So efficiency, it's good for efficiency use case, obviously. For the correctness, it's widely used. On the other hand, it's not 100% correct. So if you really need the correctness, don't use it. It's not the complexity is actually very easy to set it up, and the performance is not bad. So I told you about two problems. About like first was the clock sync, and the second one was this non-atomic log and write. So maybe first let's address this clock sync. So the clock sync can be addressed with consensus-based locking. So it's kind of consensus-based locking means we in the cluster, not on the client side, but on the cluster side, we implement a consensus algorithm so that the nodes on the cluster side, they agree on the value. So we can use Hazelcast. Hazelcast supports, Hazelcast actually implements the raft algorithm. and you can use it for like it's called CP subsystem in Hazelcast, and you can use it, and it will it prevents the split brain issue, because it always for every decision in the cluster it requires the majority to accept. So it's like a consensus algorithm. The Hazelcast is not the only one. Very popular is like Zookeeper. Is the implementation also? It provides the implementation of the consensus algorithm. So that majority of the nodes need to agree on some log operation. But I will stick to Hazelcast as I told you before. How to set it up? The client is again is the same as we've seen before. So no problem with the client. On the server side, we just need to enable the SIP subsystem, and from the user perspective, that is all you need to do. And yeah, I can actually show you quickly how it works. So this is, but actually, yeah, it's very similar to the next one. So I'll skip this demo, but you can play it on your own just to execute these commands and see how it behaves, the consensus based. And it solves the problem of this consensus based. It's like solve one of the problems of Redlog, because Redlog you can think it was like kind of consensus but on the client side, but here it is on the server side. So so the problem of the clock sync disappears, because you have on the server side, from the client perspective, you don't have any problems with the clock sync. But you still have the problem of the atomic lock and write. They are not atomic, so this is something we will need to address with the last distributed locking mechanism I will show you in this talk. But a summary for consensus-based distributed locking. So obviously you can use it for efficiency. For correctness, it's like Redlog. It's yes, you can use it. You will see people using this. You will see like and even at Google it's like it's used. They have the Chubby algorithm, the Paxos algorithm implemented with Chubby, but it's not 100% correct, as you've seen, and the complexity is somewhere in between. Performance is somewhere in between. But you see so many people using it, but still remember it's not 100% correct, because of if one process is blocked for a long time. You may say, okay, it will not happen, but it may happen. Things happens. Okay, last solution, fenced locking. So fenced locking is actually the only locking mechanism that provides 100% correctness. So you should use fenced locking if you strive for 100% correctness in your distributed system. Because fenced locking actually makes, they actually solve these problems. So you remember this problem that if one process is blocked, it may think it has acquired the lock, but actually it does not have the lock anymore. And the process can be blocked for some random time. So yeah, how to solve it? So we solve it with fencing. So instead of just sending a lock request to the cluster, we send lock and get token, and the cluster, like lock manager, will send you a token which is always incrementing. So it's a monotonic sequential number. And now the tricky part is that your shared resource, whatever it is, database, it needs to be aware of this token. It needs to be aware of the mechanism. And now if the application, if shared resource notices that there is a token which is smaller than it already watched before, it should reject it. Let's look at the diagram. So application 1 now sends a lock request. It says, okay, lock is held, you have your lease time, but and your token is 11. Now, okay, the process is blocked. Application 2 acquires the lock. The lock manager says, okay, lock is acquired, your token is 12. it writes to shared resource saying, okay, I write this to this database with the token 12. Database say, okay, it's fine. And now the application one wakes up and say, write to the shared resource and saying, I write this with token 11, but the shared resource is aware that it already seen the token 12, so it rejects it. And that is like the whole magic of the fencing, that this is finally a correct thing. So let's show it in action. So this will be the last demo for this talk. So I start Hazelcast cluster with CP subsystem enabled. So with Raft algorithm implementation. And then I will, I will show you in the meantime, I will show you the code, how it looks like. So code is it's very similar to what we've seen before. So, so it's again like from the client's perspective, there's no difference here. However, writing to the resource will take the token, and so you see here it will take the token and write to the resource with the token, and the resource needs to be aware of the token. If we start this two applications, so we should see the application 1 and the application 2 in a second, and it should be, now they are waiting for the cluster to start. So cluster needs to start before let's delete this application and start them again. So let's run application 1 and application 2 and see the logs. It's connecting. So see, now they are writing to the resource and always writing. There's never two applications writing at the same time, but they also print like the token. So the shared resource is aware what is going on here. Short cleanup. So this is actually but I really recommend you walking through these examples, then it will give you a better understanding of what's going on. So a summary of the fence locking. So this is the only correct distributed locking. However, it's very complex because you need to make your shared resource aware of the locking mechanism, which is complex by itself. In terms of performance, usually it's fine. So basically that's it. So a short summary for this talk. We covered a lot of ways how you use the distributed locking. So what is my recommendation is, like, if you don't need distributed locking, probably you can find better solutions. But if you need it, then think if you need it for efficiency, and then maybe just a single instance of the lock manager is good enough for you, like a single Hazelcast instance or single Redis. If you need like a correctness, then think how much correctness you need, because if you really need the correctness, then the only solution is actually fenced distributed locking. You can use Hazelcast for this, or Zookeeper, or some other tools. But that is how you should choose. So think about the use case first. And as the last slide, I would like to show you some resources. So the first one is the code to this presentation. I really recommend you going to the repo and just playing with all these solutions. The second one is a very good blog post about distributed locking, which is perfect. And the third one is a blog from Hazelcast, from one of my colleagues, about like how we implemented in Hazelcast and what is the Hazelcast solution for distributed locking. And with this last slide, I would like to thank you for listening. I'm sorry that I couldn't be live at the Voxed Days Romania, but But I'm with my heart. I'm with you, and I hope you enjoyed the talk and the whole conference. So thank you.